Welcome to the how-to video for electron and molecular geometry. So when we talk about different molecules such as carbon tetrachloride, with carbon tetrachloride we see it as a Lewis structure, which is just a two-dimensional object. But really this is a three-dimensional shape. And so it kind of looks more like a tetrahedron, where if we look at the ball and stick model or the space filling model, we can see that each carbon chloride bond is spread out evenly, giving us an angle of 109.5 degrees between each of these bonds. This is a tetrahedral structure. In addition, we can talk about other types of molecules where there's a central atom and then all the other atoms are connected to it. And in that, we kind of have this general structure of just A, B, where A is the central atom and B is whatever's connected to it. So usually you have something like A, B, to the n, where n could be 2, it could be 3, 4, 5, even 6. And so really we have these different types of molecular and electron domain geometries. Well, one of the things that we can do is we can predict the shape of the molecules by noting the number of bonding and the number of non-bonding lone pair of electron pairs. So we either have bonding electron pairs, which are actually participating in the bond, right? So here we could talk about like the carbon chloride bond, that's a bond. Non-bonding lone pairs of electrons, well, there's 3 of them around this chlorine. So each electron pair is termed what we call an electron domain. And being able to count up the different electron domains is probably the most important part of being able to determine both the electron and molecular geometry. Each non-bonding pair, any single bond, any double bond, or triple bond, produces a single electron domain. This is probably the most important message. So whenever we're trying to count up the number of electron domains, we just need to see how many non-bonding pairs there are, how many single bonds, double bonds, or triple bonds. Each one of those still only count as a single electron domain. When we count up these electron domains, we can then apply what we call the VSEPR model, the Valence-Shell electron pair repulsion model, which says that the best arrangement of a given number of electron domains is the one that minimizes the repulsions among them. And so we really think about it with 2 types of geometries, electron domain geometry and molecular geometry. We'll first start with the electron domain geometry, which is the arrangement of electron domains about the central atom of an AB to the N molecule or ion. And really when we think about that, we're really just looking at this table over here on the left side. Okay? And in this, we really have to count up the number of electron domains. Again, remembering that everything wants to be spread out as much as possible. You could think about these as balloons. For each electron domain, these are balloons, and they're going to try to separate out as much as possible. So if you have just 2 balloons, they spread out 180 degrees. 3 balloons, if you held them at the center, they're going to spread out evenly in this kind of trigonal planar kind of structure. 4 balloons are going to form the tetrahedral, 5 you form trigonal bipyramidal, and 6 you'd form octahedral. Try blowing up different balloons, holding those together and seeing the different structures. So whenever we're trying to determine the electron domain geometry, all we need to do is count up the number of electron domains. How many electron domains are around that central atom? So in some kind of structure like CCl4, when we really think about the structure, right, we have a carbon connected to 4 chlorines. And in that case, each single bond, double bond, or triple bond around that central atom counts as a single electron domain. Well, this is 1 single bond, another single bond, another single bond, another single bond. That's 4 electron domains. So all we do is use our table and say, okay, well, with 4 electron domains, we have a tetrahedral structure. So what I require you in my class to know is understand this table. Okay, I will provide the table. I'll give you the number of electron domains. I will give you the electron domain geometry. I will not give you the actual degrees separating. You should be able to calculate that. Secondly, we have molecular geometry, which is almost the same exact thing, except here we're looking at arrangement of only the atoms. We don't care so much about the electron pairs. We aren't concerned where those exist, but we do care about the molecular geometry. So really, on an exam, you would be given everything that's in the purple or orange colors. And so it's the exact same thing. If we go back to carbon tetrachloride, what we know is that they had 4 electron domains. and that means that we have a tetrahedral electron domain geometry. When we look at the molecular geometry, we move over to the purple box, and we say, well, how many of those were bonding? Well, the bonding domains were how many are single bonds, double bonds, or triple bonds. Well, for carbon tetrachloride, it had 4 single bonds, 4 bonding domains. It had 0 non-bonding domains, meaning that there were no non-bonding electron pairs around that central atom. That means we have this tetrahedral structure for the molecular geometry as well. And so when you go from electron domain geometry to molecular geometry, once you identify the number of electron domains, you're then just breaking up into how many are bonding, how many are non-bonding, which is now going to let you choose both the electron domain geometry, but also choose the molecular geometry. So the way that I like to think about determining the shape of the molecule, the first thing that you have to do is draw the Lewis structure of the molecule. Okay? So again, if we use the carbon tetrachloride, we'd say, okay, well, we have carbon, we have our 4 chlorines around it. So we drew out our Lewis structure. Okay. Secondly, we would count the number of electron domains. Well, how many do we have? We have 4 electron domains. How many lone pairs? How many non-bonding electron pairs are around that central atom? Well, there's 0. How many are bonding? Well, we have 4 bonding. Well, that would allow us to determine both the electron pair geometry and the molecular geometry by using the table provided. That concludes the how-to for electron and molecular geometry.